All right, greetings calculus students. Today we're going to look at a very important application of calculus, and that's solving differential equations. Now you might ask, well, what exactly does that mean? What is a differential equation? So before I get into differential equations, I thought it might be good to compare it to just a regular old algebra equation. So let's just sort of make up some standard kind of algebra equation that you might see. 4x plus 1 equal to x plus 7. So now bear in mind what this is actually asking. So what this is saying is you've got two different expressions here, and we have this unknown x. And we want to ask ourselves to solve this equation. It means what possible values of x could we plug in here that would make this equation come out to be true. So in other words, we want to think of a value of x that when we plug it here on the left-hand side, we get the exact same answers we get if we plugged in that same x into the right-hand side. And notice that for the most part, most x's don't work for that. Like, for example, if we just looked at, say, x equal 10, that doesn't work, since if you look at the left-hand side, so LHS is my abbreviation for left-hand side, so here's the left-hand side, 4x plus 1. If we just were to try, just arbitrarily, x equals 10, just pulling it out of nowhere, you would have 4 times 10 plus 1, that would be 41. However, if you try that same x out on the right-hand side, you would get, plugging in again, 10 for x, 10 plus 7 is 17. So they did not work out to be equal. It did not make an equality there. So x equals 10 didn't work. So rather than just trying different values of x randomly, you would actually solve an algebra equation using algebra. So, well, let's just see how we would do this. So again, this is just basically pre-algebra stuff, algebra 1, but just a little refresher of what it means to solve an algebra equation. So usually what you try to do is get all the x's on one side of the equation, all the non-x's on the other, I mean, just at its most basic level. So in this case, we'd want to subtract x from both sides. So when we do that, this x is going to go away, and the 4x is going to become a 3x. Please don't do what some of my algebra students do and cancel the x's and leave a 4 there. So really you would leave a 3x. So all the x's are now on this side. We move all the constants over to this side. So we're going to subtract 1 from both sides. So that makes it be 6. Of course, we want to solve for x, and here we've got 3x, so we need to get rid of this 3. So let's just divide both sides by 3, and you get that x equals 2. All right, so essentially what we've done is said that, okay, if we start with this, go through a series of algebra, we end up saying that, okay, the only possible x that could work is 2. But does it actually work? This is saying that, all right, anything that solves it would be 2, but does 2 work? So to really verify this answer, again, you can just kind of do this mentally and check, but kind of going through all the details just to make a point here. So to check it, you would actually first plug into the left-hand side. So you go to the left-hand side, plug in x to be 2, so you would get 4 times 2 plus 1 is 9. And then we'd also have to say, all right, what happens when you plug it into the right-hand side? So on the right-hand side, you plug in x to be 2, you get 2 plus 7. Hey, it's also 9. It checked out. So that, in fact, is our solution. One thing I should point out that technically you don't want to do, because it's not mathematically correct, is to plug in x equal 2 right away to both of these simultaneously and say 4 times 2 plus 1 equals 2 plus 7. I mean, yeah, technically that's a truism, but you're kind of missing the point, right? Because we want to show the left-hand side equals the right-hand side. You don't want to start off with them being equal. So you actually do want to analyze them separately, and then after you solve them, show, or evaluate them, show that they come to the same answer. All right, well, let's actually do this now with a differential equation. So a differential equation is like an algebra equation, but instead of the variable being x, where x represents a number, you still could have x's, but we also have y's, and y's represent functions. They're formulas of x's. So here's a differential equation, and notice it's got derivatives in it. So my equation is, now you can also have numbers and x's and so forth. I just kind of chose a pretty simple looking one. So we've got y squared is equal to 2y prime plus 1. And our goal eventually is going to be to solve for y for this. So we're going to try to find some form of x's where it comes out to be that if you square that formula, it comes out to be the same as doubling the derivative and adding 1. Now at this stage, we don't know enough calculus to be able to solve this yet. Now, soon we will, right? It's kind of like if you think back to algebra. Like you start off with linear equations and you get the hang of those. Then all of a sudden you bump it up a notch, and suddenly you're dealing with like x squared equals 2x plus 1. Ah, now you need like fancy factoring and quadratic formulas and zippy and so forth. So this is actually a little bit too much for us to bite off right now and solve, but I'm just going to tell you what the answer is ahead of time, and what we're going to do is check and verify that this actually is a solution. Now, what's interesting here is just like in algebra, you can have multiple solutions for x. Like if I said, x squared equals 9, there's two possible answers. Could be 3 or it could be negative 3. So there's two answers. Well, in this case, my claim is there's an infinite number of answers. And in fact, they're all of this form. So they're all going to look like y is equal to 1 plus c e to the x over 1 minus c e to the x, where c is any constant you want to be. C could be 1, could be 2, could be a negative number, could be a square root, could be any constant you want. And my claim is that no matter what the c is, as long as it's a constant, this works. So how are we going to check out that it actually works? We need to verify it's a solution. Now don't worry about how I came up with this right now. We're going to learn that in a separate video. But for now, we're just going to concentrate on how do I check to see if it works. Well, we check it the same way we check the algebra problem. So we're going to plug it into the left-hand side of the equation, see what we get, then also plug it into the right-hand side of the equation, see what we get, and verify those are the same thing. So the left-hand side says y squared. It's pretty direct. So, well, what are we claiming that y works? So just like before, we'd plug in x equal 2 and we checked it out, but this time instead of plugging in for x, we're plugging in for y. So instead of y squared, we're going to have y plus c e to the x over 1 minus c e to the x, that thing squared. Well, let's just simplify that one tad, or really unsimplify it, depending on your point of view. So when you square a fraction, you square the top and you square the bottom. So if I square the numerator of that fraction, I'm just going to use Pascal's triangle and get, the first thing squared. 1 squared is 1. Then you get double the product, so that'd be 2c e to the x. And then I got to square the last thing. So when you square that, you square the c, you get c squared. And then you also square the e to the x. Well, when you square e to the x, that just becomes e to the 2x. Because a power raised to a power, you just multiply. All right, now I could do the same thing on the bottom, but for reasons you'll see later, I'm just going to keep it as a perfect square. I'm just going to keep it as 1 minus c e to the x squared. All right, so that's what the left-hand side comes out to be. We plugged in our purported solution for y into the left-hand side. This is what it came out. Well, let's put this on the back burner now and check out the right-hand side. Plug it in for what we think the solution is for y and see what we get. So we check the right-hand side, which is 2y prime plus 1. But what is y prime? Y prime is this thing prime. This is our y, and we have to take the derivative of this. So before I go any further, let's actually solve a separate problem here. Let's look at this and see if we can figure out what the derivative is. So if I want to figure out what the derivative is, I actually have to use the quotient rule, because this is a quotient. So remember what the quotient rule says. It says you take the bottom formula, then you multiply by the derivative of the top. Well, what's the derivative of the numerator going to be? Well, the 1's going to go away. It's just a constant. You can ignore this coefficient and write it down. The derivative of e to the x is just e to the x, so we just multiply by c to the x. Then you have to subtract what you get. So it's bottom times the derivative of the top minus the top formula times the derivative of the bottom. Well, what's the derivative of the bottom? Same sort of situation. It's just going to be minus c e to the x. But then you have to take that whole thing and divide by the bottom squared. So now you can kind of see why I left that alone, because I was thinking ahead to using the quotient rule right here. But this simplifies quite a bit more. So if I want to simplify this, the bottom will just kind of keep the same. That's not really going to affect anything. I'm going to take that minus, put it with this minus, make it be a plus right here. I did that kind of fast. Well, that's all right. I think you guys saw me do that. So let me pull out the c e to the x here and the c e to the x here, because they both have the c to the x in common. So what I'm left on the top is 1 minus c e to the x from that parentheses, and then I also have the second parentheses, 1 plus c e to the x, and keeping the bottom the same. And now there's a simplification I can do right in here. Just cancel those. And in the parentheses now, the only thing that's left is 1 plus 1, which is 2. So in the end, I have 2 c e to the x over 1 minus c e to the x squared. All right. all of this, what I just got, is just the derivative. So I'm going to plug that in for the y prime. So I'm going to have 2 times this plus 1. So plugging that in, and notice that 2 times this is just going to be 4c e to the x over 1 minus c e to the x squared plus 1. Alright, so I'm still monkeying with my right-hand side. I'm kind of running out of room a little bit, so I'm going to do my little trick where I shrink this whole page down for a second. So let me do that. So we were right here. So let's go ahead and simplify that a little bit. So rather than adding 1, I'm going to write 1 in the form of making a common denominator here of 1 minus c e to the x squared over, but instead of saying 1 minus c e to the x squared, I'm actually going to FOIL it out using, again, Pascal's triangle. So 1 minus, so you double the product, right? Put the squared on there, c squared e to the 2x. So now they have a common denominator, so I can put these together algebraically with the common denominator. And let's look what we got on the top. So on the top, we still have the 1, but now we've got minus 4c e to the x, plus 4c e to the x, and then a minus 2c e to the x. So when you put those together, you just get plus 2c to the x, and then you still have your c squared e to the 2x from here. So, a little bit of algebra there, and in the end, we got this for the right-hand side. But look at this for a minute. Here's the right-hand side, and now let's go back and take a look at our left-hand side right here. I don't know if you can tell, but that was exactly the same thing. So it checked out. So when we plugged in, no matter what the c was, we checked out the left-hand side, checked out the right-hand side, and they actually came out to be the same. So our purported solution actually is correct. Now, how do we know there's not other solutions? Well, to do that, we're going to actually have to go through the calculus to figure out how we got this in the first place, which I'm not going to do in this video. But there is one last thing I want to expose you to before I leave this problem, and that is, if you look at a graph, how can you tell whether that graph is a plausible solution to a given differential equation? So I'm just going to make something up here. So let's say here's some graph, and I say, is this a possible solution to y squared equals 2y prime plus 1? And the answer is no. This is not a possible solution. This is not what this looks like. Now, I have no idea what the actual graph of these things looks like. I can actually show you in a minute using Sketchpad, but I know for sure this is not a solution. Well, how did I know? Well, there's a couple ways, but let me just show you one way right off. Is if I look at this root right here. Now, I don't know what the x-coordinate is there, but thankfully there's no x's in this equation at all, but I do know for sure the y is 0 there. So if this really had been a solution, that means that it works in this equation. Well, in this equation, when at this spot, right there, when the y is 0, what does it tell me about the derivative, if it actually matches the equation? Well, when y is 0, if you just scoot this over right here, it would say the y prime at that point would be negative a half. But look at this graph. Now, I don't know what that derivative is, but whatever it is, it's not negative a half because the slope of the tangent line there is positive. So this graph does not match this equation. So this graph is not a solution. All right, let's take a graphical look at what a solution really does look like. So right now I have the c set to be 3. So this is the graph of 1 plus 3 to the x over 1 minus 3e to the x. This is the graph, and just to do a quick little spot check verification, let's just check out the y-intercept. So the y-intercept would occur when x equals 0, so right there. And if we plug in x equals 0 here, e to the 0 is 1, so this would be 1 plus 3, which is 4, over 1 minus 3, which is negative 2. 4 divided by negative 2 is negative 2, which is exactly where that y-coordinate seems to be. Y equals negative 2 when x equals 0. Okay, well, this is one possible solution, as we verified with the calculus a minute ago. But let's see what other graphs look like. What if instead of the c being 3, what if it was like 3.4? So we can just change that c and watch the graph change. We can also make the c be lower. Something interesting happens when the c actually hits 0. So we can actually kind of check it out mathematically here first. If this was 0, then all the e to the x stuff is never going to matter. So you have y equals 1 over 1, which is just the constant function y equals 1. So you'll notice when we hit it, it just sort of switches to be that. And then in the beginning, when c is positive, it looks like this. Then it kind of flips over. And then when you get to the c's being negative, you get graphs that look like a completely different shape. It looks like this. So what would it be if we wanted to look at all possible graphs of this at the same time? So Sketchpad has a way to do this. So I'm just going to trace these different graphs as it goes. So there are the positive c's, there are the negative c's, and then here's the case when c is 0. So if I were to say, just like we do with an algebra equation, and we can make a graph of all the different x values, well, this is a graph of all possible functions, all possible solutions which solve the differential equation. And in a later video, we'll actually learn how to come up with this from scratch rather than verifying one that already is given to you.